In the previous session, we were in the middle of the concept of independent events. I recall the definition of independent events once again. Suppose we have two events, E1 and E2. We say that E1 and E2 are independent if the occurrence of E1 does not affect occurrence of E2 and vice versa. So in order to get the example of independent events, you better to take two different events over two different sample spaces, E1 from S1 and E2 from S2. Two different events over two different sample spaces. In that case, definitely occurrence of E1 does not affect occurrence of E2 and vice versa. So what is the example we have seen? If E1 is an event of getting a head when a coin is tossed, and E2 is an event of getting an even number when a die is rolled, then both the events are independent events. And in case of independent events, the result we have is P of E1 intersection E2 equal to P of E1 dot P of E2. That means intersection becomes multiplication. So this result is true in case of independent events. So if E1 comma E2 are independent events, P of E1 intersection E2 equal to P of E1 dot P of E2. Suppose I have n events, E1 comma E2 comma and so on comma En. Assume that all the events are independent events. All the events are independent events. Then in that case, the result will be like this: P of E1 intersection E2 intersection and so on intersection En equal to P of E1 dot P of E2 dot and so on dot P of E1. So this is one important point. And second point is, suppose if E1 comma E2 are independent events. If E1 comma E2 are independent events then we can make few comments. One comment is E1 complements comma E2 are also independent. So E1 complement comma E2 are also independent. Similarly, E1 comma E2 power C are also independent events. And third comment, E1 power C comma E2 power C are also independent events. So let us write all these points, very very important points. Note, if E1 comma E2 are independent events, then P of E1 intersection E2, equal to P of E1 dot P of E2. If E1 comma E2 are independent events, then P of E1 intersection E2 equal to P of E1 dot P of E2. Next, you can write this. This is for general n independent events. So P of E1 intersection E2 intersection and so on intersection En equal to P of E1 dot P of E2 dot and so on P of En. This is a generalized property for n independent events. Next, you write note like this. If E1 comma E2 are independent events, then point 1, point 2, point 3. Write all these points. Next definition, mutually exclusive events. Mutually exclusive events. Suppose we have two events, E1 comma E2. We say that these are mutually exclusive if E1 occurs, then E2 cannot occur, and vice versa. So therefore, if you want to say that two events E1 and E2 as mutually exclusive, this must be happen. So that means if E1 occurs, then E2 cannot occur, and vice versa. Let us take an example. Suppose when you take a coin problem, suppose E1 is an event of getting a head and E2 is an event of getting a tail. Now when you get head, tail won't appear. When you get tail, head won't appear. So at any time only one event occurs. In that case, both are called mutually exclusive events. Similarly, when you take die problem, suppose E1 is an event of getting even number and E2 is an event of getting odd number. So when you get even number, you won't get odd number. When you get odd number, even number cannot be displayed. So for both the events are mutually exclusive events. In this case, both the events are mutually exclusive events. Okay. Now in that case, if I write like this, P of E1 union E2. So basically this becomes P of E1 plus P of E2 minus P of E1 intersection E2. This is nothing but addition theorem on probability. Suppose when you look at this, in case of mutually exclusive events, so E1 and E2 cannot appear at a time. In that case, the probability of E1 intersection E2 becomes 0. Then I will get P of E1 union E2 is just P of E1 plus P of E2. So if E1 comma E2 are mutually exclusive, then P of E1 union E2 is P of E1 plus P of E2. That means this union is replaced by plus. So union is becoming plus in case of mutually exclusive. Intersection is becoming dot in case of independent events. These two are very, very important points. Try to understand. In case of mutually exclusive events, union becomes plus. In case of independent events, this intersection becomes dot. So when you generalize this, if I have n mutually exclusive events, then P of E1 union, U2 union and so on union En. This expression becomes P of E1 plus P of E2 plus and so on plus P of En. So this result is valid in case of n mutually exclusive events. So first let us write the definition. Two events E1 comma E2 are said to be mutually exclusive. Two events E1 comma E2 are said to be mutually exclusive if E1 occurs, then E2 cannot occur. If E1 occurs, then E2 cannot occur, and vice versa. If E1 occurs, then E2 cannot occur, and vice versa. Examples. First one. If E1 comma E2 are events of getting head and tail respectively. If E1 comma E2 are events of getting head and tail respectively. When a coin is tossed once, then E1 comma E2 are mutually exclusive. If E1 comma E2 are events of getting head and tail respectively, when a coin is tossed, then E1 comma E2 are mutually exclusive. Example 2. If E1 comma E2 are events of getting even and odd respectively. If E1 comma E2 are events of getting even and odd respectively, when a die is rolled, then E1 comma E2 are mutually exclusive. Hope you understand these examples. Note. If E1 comma E2 comma and so on comma En. If E1 comma E2 comma and so on comma En are mutually exclusive, are mutually exclusive, then P of E1 union, E2 union and so on union En equal to P of E1 plus P of E2 plus and so on plus P of En. If E1 comma E2 comma and so on comma En are mutually exclusive, then P of E1 union E2 union and so on union En equal to P of E1 plus P of E2 plus and so on plus P of En. Highlight this equation. Next we go to combinations. Very important concept. Suppose n is a natural number and r is a number ranging from 0 to n. R is a number ranging from 0 to n. This small n is a natural number. R is a number ranging from 0 to n. Now, in how many ways I can select r things out of n things? We have basically n things. And how many ways I can select r things out of n things? That will be measured by the combinations. So basically, combinations are meant for number of selections. Combinations are meant for number of selections. Let me tell you one example before discussing this. So, if I write like this, you may not understand directly. I will give you one general example. Suppose n value is 5. So, here n things are means we have 5 books. We have 5 books. Say for example B1, B2, B3, B4, B5. B4, B5. Or I can use the notation like this: book 1, 2, 3, 4, 5. So you can use either this notation or this notation. So I have totally 5 books with me, numbered from 1, 2, 3, 4, 5. I have 5 books. On one book, the number is 1. On one book, number is 2. So the books are numbered from 1 to 5. So if you ask me, sir, can you give me any 2 books of you? Then how many sequences or how many chances are there for me to give you 2 books? In how many ways I can select 2 from my side? After selection 2 books from my side, I need to give those 2 books to you, right? Now let us see how many chances are there. So I can give you book 1 and 2. So 1, 3, 1, 4, 1, 5. This is one chance. So totally when you fix book 1, the number of chances will be exactly 4. Now when you start with 2, already 1 comma 2 is selected. So 1 comma 2 is same as 2 comma 1. So don't write 2 comma 1. If I give books 1 and 2, it is same as I gave you books 2 and 1. So see, sequence doesn't matter. So you may ask me, sir, you may give me first time first book, second time second book, or first time book number 2, second time book 1. But in this case, order of giving books is not an important issue. The number of how the books are giving to you. So what type of books I am giving, I am distributing to you. That's an important issue. So finally, what books are I am giving to you? That is important issue. But in what way I am giving books to you? It's not an important issue, right? Therefore, in this case, I don't write 2, 1. I start from 2, 3, 2, 4, and 2, 5. So I am selecting book 2 fixed. So I want to give you book 2. That is fixed. So I give you 3, 4, 5 along with book 2. So therefore, in this case, I have 3 chances. Next, I can go over to 3. I fix 3. 3, 1 is already covered. 3, 2 is already covered. So we start with the 3, 4 or 3, 5. So it is 2 chances. If I go with 4, so 4, 5, only 1 chance. So total number of chances is 4 plus 3 plus 2 plus 1. So therefore 4 plus 3 plus 2 plus 1, and this is 10. Therefore I can select 2 books out of 5 books in totally 10 different ways. But if I take a large number of books, I have 100 books. I need to select 4 books out of 100. So how many chances are there? In that case, I cannot write all possibilities like this on the board or by using a pen on a paper. So it's not practically possible. So in that case, we have a combinations topic, that is we have n number of things. So suppose if I have n value 100, so I can select 0 books or 1 book or 2 books, maximum 100. So the total number of ways of selecting r things out of n things is given by NCR. So this C meant for combination. C represents combination. The number of ways of selecting r things out of n things is given by NCR, and this is given by n factorial by n minus r factorial into r factorial. So this quantity gives the number of ways of selecting r things out of n things. N is natural number. R is a number ranging from 0 to n. Even I told you why r values are changing from 0 to n. I have 5 books. So you may ask me, sir, can you give me some number of books which are having with you? Then if I am not interested, I may not give you any book. That means indirectly I am giving 0 number of books. If I wish, I may give only 1 book or 2 books or 3 or 4 or maximum 5. So if I have 5 books, I may give you 0 number of books or 1 book or 2 books or 3 books or 4 books or at most 5 books. Therefore, R value ranging from 0 to 5. Similarly, if I take general value of n, R ranges from 0 to n. The same concept we use even in case of binomial distribution, right? So therefore, I have n number of things. In how many ways I select r things out of n things? Totally in NCR different ways. NCR is nothing but n factorial by n minus r factorial into r factorial. Let us see, I have 5 books. N value is 5. Suppose r value is 2. So in how many ways I select 2 out of 5? Totally 10 chances. Now this is using this formula. So when I apply this, this is 5C2. So 5C2 is given by 5 factorial by 5 minus 2 factorial into 2 factorial. 5 factorial is 120. This is 3 factorial 6. 6 into 2. So totally 10 different ways. So manually we got 10. If I go for large numbers, do not write like this. This is easy to understand. I wrote all these points. Now this is already written. So this is always flexible. Write these points. Let n be a natural number. Let small n be a natural number. And r be a number ranging from 0 to n. Let small n be a natural number and small r be a number ranging from 0 to n. Ranging from 0 to n. Then the number of ways of selecting r things out of n things. Then the number of ways of selecting r things out of n things is given by NCR. Then the number of ways of selecting r things out of n things is given by NCR, and NCR equal to n factorial by n minus r factorial into r factorial. NCR equal to n factorial by n minus r factorial into r factorial. So let us write this example. Just write it as a question. In how many ways 2 books can be selected from 5 books? In how many ways 2 books can be selected from 5 books? From 5 books. So you write it like this. 5C2, that is equal to 5 factorial by 5 minus 2 factorial into 2 factorial. That is equal to 120 by 6 into 2, that is equal to 10. That is easy way to represent, and this is a manual way representation. Note these points also. So here 4 chances, 3 chances, 2 chances and single chance. So total number of chances is 4 plus 3 plus 2 plus 1. It is 10. Now let us write a few formulae based on combinations. NCR equal to NC n minus R. Next, if NCR equal to NCS, if NCR equal to NCS implies R can be equal to S or R plus S must be equal to N. So implies R equal to S or R plus S equal to N, because actually S value is N minus R. So here NCR is same as NCN minus R. So when you add these two, you will get N value, or sometimes NCR will be equal to NCR. So whenever NCR equal to NCS, two things may happen, either R equal to S or R plus S equal to N. Next, NC0 equal to NCN equal to 1. NC0 equal to NCN equal to 1. So note all these points. Now let us discuss one question based on combinations. Suppose the set S is 1, 2, 3, 4, 5 and so on, comma 10. Now let us discuss few queries on this. Question number 1 is, find the number of subsets of S having exactly two elements. Having exactly two elements. So what is my set? S is a set having exactly 10 elements, 1 to 10. Question number 1 is, find the number of subsets of S having exactly two elements. Second one, find the number of subsets of S having at least two elements. Having at least two elements. Next one is having at most two elements. At most two elements. This is question number 3. Now let us discuss question number 4. Find the number of subsets of S having elements 2, 3, 5. Having elements 2, 3, 5. Question number 5. Find the number of subsets of S not having elements 2, 3, 5. Last question, find the total number of subsets of S. Find the total number of subsets of S. Now let us write all questions. We discuss one by one. Now let us discuss one by one. So when you look at question number 1, find the number of subsets of S having exactly two elements. Now I will tell you one of the subset of this S. So let us solve this question. Find the number of subsets of S having exactly two elements. Let me tell you one of the subset. Suppose I can have S equal to 1 comma 2. Now every element of S1 is in S. So here S1 is a subset of S. Similarly, I can have S2 equal to 1, 3. This is one of the subset of S having two elements. Similarly, I can have, for example, 2 comma 9. So it is a subset of S having two elements. I cannot write all subsets. If I write like this, I will get more number. So instead of writing all the sets, let us see how we are getting these sets. Now we have selected 1 and 2 from this set and we have put them in the form of curly braces. We have selected 1 and 3 and we write it as a set form. We have selected 2 and 3 from the set S and we represent it in the form of a set. That means select 2 out of these 10 elements. Therefore, the number of ways of selecting 2 elements from S is 10C2. So this is 10 factorial by 10 minus 2 factorial into 2 factorial. So therefore, this is 10 factorial by 10 minus 2 factorial into 2 factorial. So this is 10 into 9 into 8 factorial divided by 8 factorial times 2 factorial. 8 factorial gets cancelled. So 90 by 2, this is exactly 45. So I wrote 3 subsets as a sample on the board. So like this, when you continue manually to write, you will get 45 subsets. So the answer for first question is exactly 45. So that is select 2 out of 10. You will get 10 C2, 10 factorial by 10 minus 2 factorial into 2 factorial. Totally, I will get 45 subsets of S having exactly 2 elements. That means what we are doing is, we were selecting exactly 2 elements from a set of 10 elements. So we were getting 10C2, that gives exactly 45. So for question number 1, the answer is this. Now let us answer for question number 2. Number of subsets of S having at least 2 elements. At least. So that means, at least means can be 2, more than 2 also. So the number of subsets of S having exactly 2 is 10C2, or at least means it can have more than 2 also. So that means it can have 3 elements, 10C3, 10C4 plus and so on. Maximum it will have 10 elements because the original set contains exactly 10 elements. So its a maximum subset will contain all 10 elements. So the number of subsets of S having exactly 2, 3, 4, 5, 6 and so on 10. At least 2 means it can have 2 elements or more than 2, but at most it will have 10 elements. So this number gives the number of subsets of S having 2 elements. This gives the number of subsets of S having 3, number of subsets of S having 4. So maximum it will have 10. So you need not simplify, but the answer for question, the result for question number 2 is this: 10C2 plus 10C3 plus 10C4 and so on plus 10C10. Write these two. 2 comma 3 comma 5 having elements 2 comma 3 comma 5. That means what is the smallest subset of S having the elements 2 3 5? The set itself, 2 3 5. So to get this set, let me tell you one case. So one of the subset of S having 2 3 5 elements is this. This is the smallest subset of S having 2 3 5. I can have like this: S2 equal to, for example, 1 2 3 5. So I can have S3 equal to, for example, 1 4 2 3 5, like this. So like this you will get many number of subsets, but I don't want to write all subsets of S having the elements 2 3 5, but to get some idea, so I wrote 3 subsets: S1 S2 S3. All these are subsets of S having the elements 2 3 5. You may have extra elements, but you must have 2 3 5 guarantee. So 2 3 5 must be there. Extra elements you can have. So 2 3 5, 1 2 3 5, 2 3 5. Now basically this is nothing but empty set union this, right? I think actually this is question number 4, I think so. So I forgot, actually this is question number 4. We will go back to question number 3. Once I discuss question number 4 and 5, I will go back to question number 3. So find the number of subsets of S having elements 2 3 5. Now this is question number 4. So in this case, S1 is this, S2 is this, S3 is this. So this 2, 3, 5 can be written as empty set union 2, 3, 5. Now this we can write it as singleton 1 union singleton 2, 3, 5. This we can write it as set of 1, 4 union set of 2, 3, 5. Now when you look at this, this is a subset of S having 0 elements. So basically we call it as null set or empty set. This is a subset of S not having 2, 3, 5. It is a subset of S not having 2, 3, 5. A subset of S not having 2, 3, 5. A subset of S not having 2, 3, 5. A subset of S not having 2, 3, 5. Therefore basically this is subset of S not having 2, 3, 5 union the set 2, 3, 5 like this. Therefore to get the result for this count, what I do is find the total number of subsets of S not having 2, 3 and 5. So that means in order to get the answer for question number 4, let us try to get the answer for question number 5. So in that case you will get the answer for question number 4 very easily. I hope you understand these points. Actually what I am expecting is the total number of subsets of S having the elements 2, 3, 5. So this is a subset of S having 2, 3, 5. It is a subset of S having 2, 3, 5. It is a subset of S having 2, 3, 5. So extra we have 1, 4. Extra 1, extra we have 0 number of elements. So like this you can have many number of subsets. Actually I want that count. But manually to get idea, I wrote 3 of subsets of S having 2, 3, 5. So S1, this we can write it as null set union 2, 3, 5. This we can write it as singleton 1 union 2, 3, 5. This we can write it as set 1, 4 union 2, 3, 5. So basically this is a subset of S not having 2, 3, 5. It is a subset of S not having 2, 3, 5. It is a subset of S not having 2, 3, 5. Therefore how I get subsets? Subset of S not having 2, 3, 5 union set 2, 3, 5. Therefore to get the count for this, at first I will try to concentrate on subsets of S not having 2, 3, 5. So therefore I will take S1 equal to S minus set of 2, 3, 5. So therefore this is S minus set of 2, 3, 5. So therefore this becomes set of 1. This is 2, 4, 6, 7, 8, 9, 10. 8, 9, 10. Therefore here the number of subsets of S1 is, see how many elements are there in S1? Only 7 elements. 1, 2, 3, 4, 5, 6, 7. So the number of subsets of S1 is 7C0 plus 7C1 plus 7C2 plus and so on plus 7C7. This is 2 power 7, totally 128. I will tell you how I got this. So when you look at 7 elements, its a subset may have 0 elements, that is empty set. Its a subsets may contain exactly 1 element. Its a subsets may contain 2 elements or maximum 7 elements. Therefore the total number of subsets of S1 is 7C0 plus 7C1 plus 7C2 plus and so on plus 7C7, that is 2 power 7. Directly we have some result. The result is like this: NC0 plus NC1 plus NC2 plus and so on plus NCN. This is nothing but 2 power n. This is useful result. So therefore the total number of subsets of S1 is 128. But basically these 128 are again subsets of S, because S1 is a subset of S. This is a subset of S. So we have one result. Suppose A is a subset of B. This is subset notation. And B is a subset of C. Then A is subset of C. A is subset of C. Therefore here S1 is a subset of S. But these 128 are subsets of S. Okay. So therefore the total number of subsets of S1 is 128. They become again subsets of S. Therefore there are exactly 128 subsets which do not contain 2, 3, 5. Which do not contain 2, 3, 5. So therefore, the total number of subsets of S not having 2, 3, 5 is 128. Why we got 28? I am subtracting 2, 3, 5 from S. So therefore, S1 contains only 7 elements. In the set S1 itself, we don't have 2, 3, 5. If the original set does not have 2, 3, 5, how its subsets contain 2, 3, 5? So S1 is not having 2, 3, 5. Automatically, any one of subsets of S1 do not contain 2, 3, 5. So the total number of subsets of S1 is 128. These are again subsets of S not containing 2, 3, 5. Therefore, the total number of subsets of S not having 2, 3, 5 is 128. So to get the answer for question number 4, include 2, 3, 5. Make union 2, 3, 5 to all these 128. Therefore, sets are different but count is same. So the total number of subsets of S having 2, 3, 5 is 128. The total number of subsets of S not having 2, 3, 5 is again 128. So therefore, this 128 gives the total number of subsets of S not having 2, 3, 5. But to get number of subsets of S having elements 2, 3, 5, include 2, 3, 5. So sets will be different but count will be same. So answer a question for question number 4, the answer is 128. Even for question number 5, the answer is 128. So this is the logic. So work out these points.